While Klaus is setting up, I think we can start introduce him as the beginning of this session. Welcome to the afternoon session, first one. And I would like to introduce our invited speaker, Professor Klaus Wehrle. He has been very internationally well known for his work in network protocols, formal methods, and reliable transmission. So he has won the prestigious ERC award. ERC grant is the most prestigious European grant in the EU. And he is currently the chair professor at Aachen University and also department head for the computer science. So he's also responsible for the DFG, the German Science Foundation priority program on CPS, CP network, okay, for cyber physical network.
Cyber physical networking, yeah.
Okay, so he will give us the talk from reflexes to in-network processing, okay? Welcome.
Oh, thanks Xiaoming for the kind introduction, and thanks for giving me the opportunity to talk here. I hope I can meet the time limit. I try to assemble some slides which go into an area where we are quite active in the last 3-4 years, which is, goes beyond the typical networking that we are doing in the internet, mobile communication, and so forth. So it goes into the industrial field. And that's what we are called cyber physical networking. And I want to talk about the quest to enable and achieve very ultra low latencies. And I'm not talking about 5G and also high reliability in those networks. Let me start with this. So what you see here is what I typically, if I summarize the last 50 years of communication, I always say there are several evolutionary steps in communication systems. So from the good old internet 50 years ago, over then where we connected people with each other, later then they are mobile, and then when human beings are communicating with machines to put or retrieve information, or if they interact with the world just to get an impression of the status somewhere, traffic, temperature, whatever. So the common thing in all these evolutionary steps from the good old internet up to mobile communication and Internet of Things is that the human being is an integral part of the communication loop. So human beings either interact with web servers or they interact with sensors in the physical environment, but still the human being is an integral part in all these evolutionary steps. So since human beings are slow compared to communication systems, latency was not a big deal so far. So everything below 20 milliseconds was not really a big deal. And also reliability was not a big deal, because when an error happened, of course, you were a bit upset if your app crashes or your mobile phone crashes, but you could handle it, you could reset it and so forth. What I claim is that the next evolutionary steps in communication systems is different. It's different in the sense that the human being is not anymore part of the communication loop. So what we want to do here is, what you can see here indicated by this robot here is, with machines, with servers, with computers, we want to control physical processes, not just observe them as in the Internet of Things, but we really want to control them. Autonomous driving, production sites, and so forth. And the human being is not anymore part of the control loop, so we need high reliability. And if we want to achieve a high precision, we need to have ultra low latencies. That's especially a feedback from control people, control theory people, that they give us. And I want to focus on that use case a bit more in the coming talk. Okay, so if we have this challenge of achieving ultra low latency, how can we do that? So let's take a look at the architecture that you learn in university or in school about how the internet is designed. It's this typical layered architecture. And we can see that the blue part, the network itself and the networking layers, they are only dealing with transport. transporting data. They do not look into application payload. We never had that except for bit sensor networking. So typically we do a transparent forwarding. But the problem is if we have an application like this controlling this robot and we want to achieve ultra low latency, actually the physical distance and the latency becomes an issue. So what you can see here is if you sense the status of the robot, you have to communicate it through the stacks horizontally and vertically. Then a decision about the reaction is made, and that is then communicated back. So the physical distance is actually our biggest problem in achieving ultra low latency. So the first solution to circumvent that is, of course, reducing the physical distance. That's actually what 5G is doing. They do not invent a technology that is faster than speed of light. They just push the controllers, the processes nearer to the base stations. So they do edge cloud and other modern terms of just pushing the control process nearer to the process. But still, that is not the final solution. And that's what we try to investigate, how we can even improve that in order to achieve much lower latencies. So let's take again the look now not on the horizontal latency, but also on the vertical distance that we have in the stack. So again, the same thing, we sense a value, the status of the robot. It's communicated through the different networking elements through the blue part. Then, and that's very important, then we have this problem of our layered architecture that the control process is completely abstracted from the network. So it does not have any idea of what is going on in the network, and it cannot really interact with the network because it's just another application for us. And so this abstraction between the networking layers and the application layer, especially here the controller, is a bit a problem for us. And that is, then the decision is made, and then the acting value is communicated back. And the result you can see. So we typically use this inverted pendulum as a toy example. In this case, it's simulated. So this is a typical use case from control theory to judge on the quality of control of physical processes. So at the moment, the latency of the reaction is too high in order to get this pendulum stabilized. Okay. And this was the starting point of the initiative that Xiaoming mentioned in the beginning. It's the priority program on cyber-physical networking. So how can networking and control theory be improved in order to achieve better control of physical processes? And our goal is a co-design of networked control. So we want to get rid of this abstraction here and intertwine the processes that are going on in the control application and in the network so that they can react. Okay, so how do we do that? Again, our example here. And often when we have a problem, we think about, isn't there a good analogy? Can we find a good solution somewhere, for example, in nature, or as I show here, in the human body? So if you want to have fast reaction, reflexes are a typical thing that we have in the human body. So for example, if your hand comes near to a hot surface, you immediately take it back. And that's a decision that is not made in the brain. That's a decision that is made in the nerve system already. So that's quite similar to our problem. The communication latency is too high that the brain can decide, take your hand back. So it's already decided on the communication path. And that led us to an idea that we call reflexes. And the idea is to split the horizontal path up into a low latency data path and into a latency tolerant control path. So we are pushing control or activity in general into the network. Of course, that harms our typical layered architecture, but let's see what we can do about it. And that is the challenge that we are currently pursuing here at COMSIS. We try to push in-network processing as far as possible and can see what can we do about it. For this specific use case, the co-design of communication and control, we tried to take the tasks of the control theory. So how to stabilize an inverted pendulum. What do you have to do in order to do that? So that's a PID controller here. And we take the communication task. So in this case, we have the MAC protocol, but also other things that are related to communication, and try to somehow put that and push that into the network. And when we started with this, SDN was a new technology that came up in networking and that offered us new possibilities actually to do something in the core of the network. So far, these were black boxes. You could just send them some routing decisions or some routing tables or some filter rules, but not more. With SDN, it was a starting point of doing more activity in the network. And we tried to actually derive from the control tasks simple rules that describe how to stable the pendulum. So tried to describe that a bit like SDN rules. It's not really possible, but it's at least a bit near to it. And we tried to do that for the communication task, which is a bit more feasible. So we have a similar, let's say, language, how we describe that. And then we try to combine that with simple rule sets, which we then push into the switches. That was at least the idea how we started with this co-design of communication and control. I have to admit, it did not really work because SDN actions were not really suitable for that. So it was a bit disappointing. Our backup plan was to just simply pre-compute every possible action that you can think of, but that actually bloated the rule tables of early SDN switches, so it was also not really feasible. But shortly after we tried that, there were more modern hardware, or there was more modern equipment available, which is in some sense programmable. So for example, FPGA NICs or FPGA switches, smart NICs, or the modern Barefoot or now Intel Tofino chipsets, which actually offer programmable pipelines on in-network components. And that actually then paved the way to realize this reflex concept, and then we finally could do it. So to dive a bit more into that, you can see here the physical process, here the cloud, where the controller sits. And what you can do is, if you have the values from the physical process, they are sent to the compute platform. And then, of course, you can decide, how do I compute now the decision how to stabilize the pendulum? You can do that on an end host. Then, of course, you have to traverse the whole stack until the user space. Then you make the decision. So as I showed before, so that's quite slow, but very flexible in computation. You can also do it in the kernel, which is a bit faster because you have less vertical latency. But the kernel is always a critical area to do dynamic tasks. The next step were smart NICs, which are nicely programmable and actually run at a high speed, so even less vertical distance, up to doing it in the switches, where you can do the processing of our reaction, which is, compared to the reflexes, it's a simple reaction, but it should be fast. You can already do that in the switch. So we have different approaches how to do packet processing or payload processing already in the network. And the thing is, the deeper you go, or the lower, the more you go down here, the faster and more predictable the computations are. But the more restricted operations you can do. For example, in a Tofino switch, you cannot do floating point operations. You cannot do divisions. You can do a bit multiplying, or with some tricks you can do multiplying, but nothing more. On the other hand, the higher you get in this list, the less computational restrictions you have, but the more unpredictable and slower the executions are. So the runtime and the processing time varies. So this was the realm where we tried to dive in and try to find out a bit more. And from this example that I showed you before with the pendulum, we managed to do these reflexes. We pushed them into switches. And then we did not only shorten the horizontal latency or the horizontal distance, but we also shortened the processing time significantly. So as you can see here, and this is not a still image, this is a video, the pendulum is nicely stabilized. So it just should indicate that you can reduce latency and then you can achieve a much higher quality of control and a co-design of communication and control, and to achieve much higher precision as you have been before with this abstraction that I showed you. So this was the starting point. Again, you can say, as I like to indicate again, I like to see this as a general framework. So you have this low latency data path between the physical process and the switch where the computation, this very simple computation is done. And you have the control path where then the rules, the computations, the state, and maybe also the mobility is controlled by an edge cloud. So this is latency critical and this is not so latency critical. Okay. So this was the starting point. We have another big project here at the university because we are a very engineering university. We have lots of mechanical engineering, and we have then tried to apply this concept to further use cases. So one is, for example, the process of arc welding robots. So they are welding metal pieces together with a light arc, a very heavy physical process with lots of control loops inside, where you have to decide in single-digit millisecond latency. And the sensors you have here are actually cameras, the current from the light arc, and the actuators are robot positioning and so forth. We are not really there yet to control this process, but we are trying to get as near as possible we can do. Another use case is mobile robot cooperation, not just this toy example like here, but I show you a video later with a real use case where you also have different control loops. But interesting is, what requirements do you have here? So you have mobile components which try to cooperate. So one interesting aspect, for example, is the positioning of these components, finding out where they are. So there you have indoor coordinate systems, and these are very important that these robots can cooperate. I explained that in the next video, on the next slide. So there are very different sensors and actuators, but all of them require real-timeness, fast processing, and low latency. Okay, so yeah, here's the video. Let's just, before I start, let's explain what happens. So we have here a mobile component which starts to move in a second. We have here something like a truck cabin, which doesn't have a window shield here. And what happens is that this cart gets the cabin, moves it here to this robot, and then from, I don't know, somewhere, the windshield comes, and this robot has to place it in here. And here we have to be very accurate in positioning the physical components. And in order to be able to do that, we have an indoor positioning system. In this case, it's a laser tracker, which tracks these components and gives feedback where they are at the moment, and such that they can cooperate in a very precise fashion. As you will see now in the video, yes, it runs. I hope you can see it. But as you can see in the video, the components are quite slow. So in order to get an efficient production, they need to be much faster. But the problem is the laser, the results from the laser here that tracks the distance to these components, it's first, it's pre-processed in a computer, and then when you have the coordinates of these components, they are sent then to the controller, which controls the movement of these things here. And in that process, you have a transformation of coordinates, which I explain a bit later. So intermediate processing steps which have to be done. And these are actually quite slow. because they are done in the cloud. And what we try to do is we try to push these computations into network elements in order to speed up the process much more. And if we are successful, then this robot can move at 10 times or 50 times of its speed. So getting the actual physical position of these devices and coordinating them is at the moment the bottleneck. Okay, so let's move forward to the next slide. So here you see an illustration of this. So again, here's the mobile robot or the components. This is the laser tracker, and then the results from the laser tracker is first going to this machine or to this computer, which is nearby. But it's just the interface that then the spherical coordinate system of this one is then sent to a cloud where the coordinate transformation is done to, I don't know, I have it on the next slide how the coordinate system is called. And then this can be used, the absolute coordinate system can then be used by the control of the robot in order to control the robot then. So we have different intermediate steps and they are too slow at the moment. Yeah, and our goal is to put some code here, some reflex or some program here in order to speed the whole process up and do the whole pre-processing already in the network. Okay. In order to do that, yeah, here I have it, the conversion from spherical coordinate system to Cartesian coordinate system. It's a bit like this calculation here. So you have the distance that is measured by the laser beam, and you have the angles of the laser beam from various axes, and that must be converted to the Cartesian system. And as you can see this here, you get immediately the impression, what? You want to do that in a switch? Yes, we want to do that, but it's at the moment, it's tricky. But that's actually what we want to do. So we want to find out how far can we get, how far can we push that, and what gain can we get out of it. So what we do is, the first thing is, so for example, in a SmartNIC or in a Tofino switch, we do not have floating points. So we have to switch to fixed point arithmetic or even integer arithmetic. So that's the first restriction we have to do. And then we have to, we cannot calculate sine and cosine functions in a switch. So what we do is we approximate these functions and just push them into tables like this one. So where we have the pre-processed sine values in a table, and then we just get the angle from the sensor, and then we just check, okay, this is this angle is then this sine value in a fixed point arithmetic. The problem here is actually, but then that this table becomes incredibly high if you want to have, or incredibly large if you want to have a very high precision. So this was a showstopper in the first try, but then one of my students found this nice trigonometric rule here that you can actually split up the angle here and then calculate from two values, or with this function, then calculate the sine function of a plus b. And the nice thing is then we can actually split up our pre-processed table into, let's call this the big angle, so something like 5 to 10 degrees, yeah, with various values. And the small component, I show you in a second how it works, which stays fixed then. So for example, if we have a sine, if we want to calculate the sine value of this angle here, and you can see this is a very precise angle, it would be this, but we cannot compute that neither in fixed point arithmetic nor in a pre-processed table. This table would be incredibly large. So we just split it up into the larger part of the angle. We check that in this table, and then we have the further part, which is always the same. It's the high precise part of the angle, which we keep in this table. And then with this calculation here, we can then estimate the sine value of this high precise angle here. And the nice thing is, of course, you would say this can be a large area here. So if you have 5 to 10 degrees of angle, this becomes a large table. Here comes again into the game what I said before. We have the slow path and the fast path. So if the laser tracker moves, the cloud then updates this table to the angle where the laser tracker is at the moment. So we can keep this table considerably small. Okay, so with a lot of tricks, you can actually do such a calculation in a SmartNIC or even in a Tofino switch. Okay, another example that we did is, it's not the light arc welding robot, but we use a toy example in the lab. But it's the same challenge. So you have a white line and you have a car which follows this white line, and you get then the image from the camera. And then if you want to process in the switch, do I have to move to the left or to the right? Sounds interesting, but is it actually feasible? And if you have a high precise image, of course, you know that the image is split over hundreds of packets, and doing a complex processing actually over hundreds of consecutive packets in a switch, which probably are not even in order or come at various times, is not really feasible. But here also it helps to check the problem, to reduce it to its core. And what we managed to do this is to actually reduce it to a very simple image analysis. Now my animation works. So we just have to find the gradients here between the white line and the gray carpet here. And this we actually managed to do in a Tofino switch quite, with doable effort. And so we could do the simple image analysis also in a Tofino switch. Okay.
Okay, we have 3 to 4 minutes in total for your talk, but
I have to speed up. Okay. Sorry. Then maybe I leave this out. This is data stream processing. That's actually a well-known application. So in the scenarios I showed you before, in this Industry 5.0 scenarios, we also have lots of sensor values in the production machines, and they are pushed to the cloud where they are analyzed it with all this data science and AI to do intelligent production. But actually, it's a hell of data that is transported there. We have also a use case here. And what we do is, after the first analysis, we just push filters into the switches to reduce the amount of traffic and to do pre-calculations, pre-aggregations, pre-filtering, and so forth in the network in order to reduce and to do early computations already in the network. And that improves the network load tremendously, and also the load on the cloud. Okay. So what I actually want to motivate is this architecture that I told you before, that you have here a physical process, you have data at high rate, at high volume, or at high precision. You do already pre-computing, pre-processing, or controlling in the network, and then you can give fast control actions, fast feedback, and you have this low control loop here with the cloud where just updates are done as the angle table updates, or you do state management or mobility and so forth. And this is something that we try to push at the moment, also in the IRTF, where we have the COIN research group, Computing in the Network, where we presented these industrial use cases and which are now taken over by the research group as an important area where the research group will focus on in the next time, and where we are also discussing issues like transport issues and so forth. Okay, another thing that I want to show in the last 2 minutes is also performance prediction of such things. So because performance of computations in the network is an important topic. So here I do not have an industrial use case, but a typical network function as we have it in switches for example, a firewall or intrusion detection algorithm that runs on a Tofino switch or on a software-based switch. And in the ERC project, we are doing a lot of analysis how to make these programs bug-free. So we do symbolic analysis. I'm not talking about that today. But what we get out of the symbolic analysis is a complete execution tree of this network function here. So we get feedback if there are bugs in it and can fix them. But when we are done with it and we say, okay, the correctness of the network function is now proven, what we can also do is we can take all the possible instruction chains of this network function. And then we have models of the instruction processing, the caching, the CPU. And if we have traffic patterns, what we then can do is we can convolute both and do very fine granular prediction of the performance of these network functions. So what you see here, I have it on the next slide. What you, for example, can see here is a firewall network function, which is implemented as a decision list. And you can see here the CPU cycles that the different paths are taking and a CDF of their, how often they occur. And the green curve shows what we have predicted before this code has even been deployed about the performance. And the blue curve is showing the measurement. So you can see it nicely fits our predictions. So we can very fine granular predict what is the actual or resulting performance of this network function if you would apply it in a switch. You can see it also here with a different network function. It's also a firewall, but implemented as a decision tree. And you can see it nicely predicts the performance behavior. So operators do not need to have fear anymore that packet processing or active elements in a switch will slow down the processing. And you can also apply different traffic patterns on it and then see how the network function behaves and can actually pre-compute its performance nicely. Okay, so as a summary, what I want to motivate today is that on-path computations have always been considered harmful in networks. So there was an initiative 20 years ago about active networking. It disappeared. People have been afraid of erroneous, slow, and unpredictable behavior in the core network. And of course, that was a considerable case. But these days, latency matters more and more. We cannot always allow us deviations via cloud and data centers because they are quite costly. If we first have to move the data to a cloud, process it there, and then get it back. And the type of computation that often is needed is not really complex. So, and it's not too lengthy. So the examples I showed with the coordinate transformation is even already a weird example. So often it's just simple rules like filtering, additions, some decisions, and so forth. And there are more and more hardware components available that can do that do more than just packet forwarding, counting, and dropping. They can do decisions. They can do simple computations. They can do iterations and so forth. And they can do that at 40 or 100 gigabit line speed. And they have several parallel processing lines in that. So the hardware is actually getting better and better and supporting this. And of course, there are also now better methods to predict the software, the behavior of these components, to prove that they are error-free, to predict the resulting performance, and to ensure that the code actually does what you want it to do. So that is actually what is driving us at the moment. It's still far from practical application in a core network, but our goal is to find out the limits of this radical technique and to push it as far as possible, and of course to also give feedback to the next manufacturers, of the next hardware components, what probably would help if they could integrate it. So this was a little overview over in-network processing with a, let's say, exotic use case from production and industry. But actually, that's a big field and yeah, a lot of problems that could be solved if you think out of the box. So thank you very much. I'm happy to answer your questions now. Do we do them here or in the chat or?
Thanks. Firstly, thank you very much for your. I don't see any questions in the chat, but we can have 1 or 2 questions for the audience. Any questions? Raise your hand and.
Yeah, raise your blue hand.
Yeah, there's should be a reaction. Yeah, somewhere how to. Okay, I have no idea how this button is different from the normal Zoom.
Yeah.
Okay.
Okay.
Any questions?
At least I see a thumb up.
Okay, I got a question. This industry IoT is very much a rich area to work on, but as you said, the control function and also the required computation is quite small scale. Therefore, is that really indeed necessary to deploy such a 5-layer or 2-layer switch of functions rather than just put some onboard devices to do the computation, but only release some analytics result to the backend servers? Yeah,
that's a good question, Xiaoming. I always get this question. Let me just go to the slide to answer that, because I showed you a very simple use case. What often happens is, so if you have just one source of input and one action, so if you just get
very limited number of action possibilities.
Yes. So it becomes very interesting if you have multiple sources of sensor values and multiple sources of input, and you need that information also at multiple points. Then you cannot do it anymore locally. And since these factories are getting more and more equipped with mobile components, you cannot just place a computer somewhere. So we have to talk about wireless communication here. And then I would assume I do these computations in the access points or in the 5G base stations, but not directly at the machines because they are heavy.
Yeah,
they change a lot. And for example, such a use case as I showed in the movie, I was also surprised when I saw that the first time. In such a robot, you have something like 6 up to 10 sources or sensors, and they are not connected via one cable. They are all individually connected. So you have to bring them together in a switch.
Okay.
And that's why I always say the switch is, in my opinion, the source of or the nearest point to the physical process where you can push that. So for example, the controlling of the robot is one interface. The arm and the actuator here are multiple interfaces which have individual network interfaces. The movement here and maybe some positioning and other sensors also are individual components which are not directly connected. They are then connected at the cloud controller.
Okay, this explains very well. Yeah. I think due to time limits, we are exceeding about 8 minutes.
Oh, sorry.
Yeah. So thank you very much again, Klaus, for your inspiring talk. And I think if further questions, we can also further on continue in the Vura app, because that is permanent entry, I think.
And if not, send me an email. I'm happy to answer.
Yeah, email is
although I have lots of emails.
Okay.
Okay, I stop sharing now.
Okay, thank you. Let's go to the second speaker. I think it is Ning, right?
Yeah, I'm here.
Yeah, Ning, can you enable your screen? And before that,
I will share.
Briefly introduce him to everybody. And he is a faculty member at Harbin University of Harbin Institute of Technology in China. He got his PhD from Spain in 2018. So he works on edge IoT and so we'll work on different areas about wireless and edge computing. Okay, so he has a lot of publications in different venues, including journals and conferences. Can you use the share screen function, Ning?
Okay, thank you. I will share my screen and
yeah.
Okay.
Let's welcome to his talk then. Yeah. Search tree-based SDN candidate selection.
Can you see my screen at this moment?
Yeah.
Okay, I will begin my...
You can make it bigger, the full screen.
Okay. Yeah, okay. I will begin the presentation of my papers in ICNP, and the title is the search tree-based SDN candidate selection in hybrid IP and SDN network. Firstly, I will introduce what is the hybrid IP and SDN network and why we use SDN, introduce SDN into the IP network. Firstly, as we all know, the link failure recovery is very important to the internet because it's guaranteeing the reliable and the security service for the users. But in the previous works, the approaches used to protect the link failure has some disadvantages. But so in this year, some people introduce the SDN switches into the IP networks to protect the link failure. I mean, this means that we use the SDN switch to protect the link failure and recover the link failure quickly. But there will be at this moment there have some algorithm has been proposed for introduce SDN switch into the IP networks to protect the link failure. The other grid-based algorithm. Before introduce the grid-based algorithm, I will explain why we need to introduce the SDN into the IP network, because someone will may say that why we deploy or replace all the switches in the IP networks into the SDN networks to improve the link failure, to protect the link failure in the IP network, but this will be expensive, or sometimes it's impossible, because if we replace all the switches in the IP networks into the SDN switches, it will be spend a lot of times and as we know, the SDN switch is very expensive than the traditional IP switches. So this is why we need to minimize the SDN switch in the IP networks and protect all the link failures in the IP networks. So this is the purpose of this is the purpose of this paper. So since there have already some algorithms have been proposed for protect the link failures based on the SDN technologies, they are mainly the grid-based algorithm, but they have some disadvantages. I will be introduced in the next section. So this is the reason why we propose a new search tree-based SDN candidate selection approaches for the IP and SDN hybrid networks. So the contributions will be introduced in detail in the next section, and first, the network model is simple. This means the networks that we used in this paper, and this means the nodes and in the network, and this means bidirectional links in the network. The bidirectional links means that both node 1 and node 2 can communicate with each other. So in these networks, if the link between node 1 and node 2 failure, and both node 1 and node 2 will know that the link between these two nodes are failure, and they will find another way to reroute the data in this link. So in the IP and SDN hybrid networks, there are in the previous works, which has been defined in reference 10 and 11. There are two principles that we design the SDN switches into the IP network. The first is that the shortest path from the route I to the SDN switch K does not include the field link. I mean, if the link between node 1 and node 2 failed, if we choose node 10 as the SDN switch, and the node 2 can reroute the state to node 10 and does not use the field link node 1 and between node 1 and node 2. And this is the first principle. And the next principle is that for each affected destination, because if the link between node 1 and node 2 failed, and a lot of nodes will be affected by the link field of this link. So for each affected destination, there exists at least one next hop of switch K, and the shortest path from edge to the affected destination does not include this field link. And these are the two principles that we choose the best place to display the SDN switch to protect the link failure in the IP networks. So in this slide, we will introduce the traditional, not traditional, the grid-based approaches, and the grid-based approach is the only approaches that can solve this kind of problems. And the grid-based approach is very simple, and we assume that there are 10 SDN candidates, SDN switches in the network, and I mean there are 10 nodes can be replaced by the SDN switches, and each candidate SDN switch, for example, the first SDN switch, if it can protect the link failure of link 1, then this value will be set to 1 in the table, and otherwise it will be set to 0 in this table. If the value is 0, it means that the SDN switch 1 cannot protect the link failure of link 3. So this is the table construction, and if once we get this table, and now next we will calculate, we will select the minimum number of SDN switches in the network to protect all the link failure in the IP network. I mean, this 10 place are the candidate place to deploy the SDN switch, and our propose is to choose the minimum number of SDN switches in this 10 place, which can protect all the link failure in the network. And for the grid-based approach is like this. First, it will calculate the sum of the column of each column. Calculate the sum of each column and find the largest one largest column which has the highest value. For example, if column 8 has the largest value, and then the place 8 will be chosen as the first SDN place to deploy the SDN candidate and SDN switches. And if once this column is chosen, and they will be this column will be deleted from table, and all the rows in this column which the value is 1 will be also deleted from this table. I mean, for example, if once the column 8 is chosen, and then column 8 will be deleted from this table, and the row 1, row 3, row 5, 6, and all the value which is equal to 1 will be also deleted from this table, and this process will be repeat until there is no column and no rows in the table, and then the chosen column will be the place which we can deploy our SDN switches. This is the process of the grid-based approach, and it's very simple, and but it's effective to find the place to deploy the SDN switch to protect the link failure in the IP networks. But it has some problem. First, it cannot, based on the grid-based approach, it cannot find all the feasible solutions. I mean, for example, based on the table and the grid-based approach, for instance, the feasible solution 83917, 8383917. This 5 column will be chosen, but except for these 2 feasible solutions, there are still many other feasible solutions, such as 8, 7, 8, 9, 3, 10, or other feasible solutions. But based on the grid-based approaches, they cannot find all the feasible solutions. This is the first disadvantages, and the second disadvantage is based on the grid-based approach, we cannot guarantee that each time we always can find the best solution. I mean, based on the grid-based approaches, we cannot find the solution which always has the minimum number of candidate switches. For example, in the table shown below, the solution 2-1 is better than 3-1 because the number of candidate switches in this solution is smaller than in this solution. But the grid-based will be choosing this solution as their as the final solution. So this is the second disadvantage and also problem of the grid-based approach. But for the 3 problem is that for each link failure, for example, the link between node 5 and node 8 failure, and there are 4 SDN switches can protect this link failure. So which SDN switch we choosing to reload or not reroute our data to has not been investigated in the previous works. So this is the third problem of the grid-based approach. So summary, our problem will be solved in this paper is that how to find all the feasible solutions with low computation complexities, and how to choose the most appropriate solution as the final SDN switch deploy locations, and how we can guarantee that the proposed approach can always find the optimal solutions. Finally, how to choose the SDN switches for each link failure to reduce the transmission delay of the transmission cost. So we proposed our tree-based algorithms. Our tree-based algorithms collect the informations. As the tables showing as in this table, as the information shown in tables, we can find that the link 9 and it is only protected by one SDN switch. It's 9, and the link 11, 20 only protects by SDN switch 8, and the link 14 is only protected by link 7. And these 4 links only protects by only one SDN switches. This means that if these 3 SDN switches are not chosen in the final solutions, and these 4 links will be.
Reminder, Ning, you have 5 minutes, including Q&A left.
Okay. So it means that this SDN switch 7, 8, 9 will be must be chosen, and this. Okay. This so first we will choose 7, 8, 9 will be as our first level of search tree, and the second level of the search tree is based on the same process as we introduced before, and based on our search tree, all the feasible solutions will be found, and the optimal solution also can be found based on our search tree. And if once we get the feasible solutions, we calculate the average repair path of each solution and the load balancing degree of each solution. Based on these 2 parameters, we choose the best SDN candidate switches for each link failure. And this is the performance evaluation and results. And our proposed approach has some advantages over the previous works. Okay, thank you very much.
Thank you.
Okay, thank you very much.
Is there any question? Because I don't see anybody who raised hands or put on comment. Q&A. Okay, so may I ask one question? So do you analyze the complexity about your algorithm? Complexity.
So sorry, I cannot hear you clearly.
I mean the complexity about your algorithm. Can you did you do the analysis? Yeah.
No. At this moment, we have not finished. We have not finished the analysis. This is what we have doing now, and our proposed algorithm is a little complexity than the previous works, but it's not so complexity, and it is. This is what we done now.
Okay. Is there any other questions or comments? Okay. So if not, thank you very much again for your talk, and let's move to the next speaker.
We
are catching up the time. Felix, can you get prepared to share your screen?
Yep.
And I would also briefly introduce him. Felix Weinrank is a PhD student at Münster University of Applied Sciences in Germany. And he is working on transport protocols and low latency internet communications and network emulation. Okay.
Yeah, hello everyone. This work has been done by me, Michael Tüxen, and Erwin P. Rathgeb from the University of Duisburg-Essen. And today's agenda, we will get a look into RAG for SCTP. RAG is an error recovery algorithm developed by Google. We will see this later. But before, I will briefly introduce you into the SCTP transport protocol, then the default loss recovery for SCTP, and then I will introduce you to the RAG algorithm, how we ported it to SCTP. We will have a look at the performance evaluation and which modifications and improvements we have made to the RAG algorithm to best fit it into the SCTP model. The SCTP protocol, SCTP stands for Stream Control Transmission Protocol. Like TCP, it's connection-oriented, reliable, but in contrast to TCP, it's message-oriented and not stream-oriented. It provides network fault tolerance, supports multi-homing, which means you can have a single association, which is the name for a connection in SCTP terms, and you can have multiple paths. For example, one path via mobile or one path via Wi-Fi. And if one path fails, the association automatically switches to an alternative path. Which this is one of the key features, and SCTP has originally been designed for signaling and telecommunication networks. This is where you typically have multiple paths and you don't want to have a failure. But now it has evolved to a multi-purpose transport protocol. It is, for example, used in the WebRTC data channel stack, where it's the underlying transport protocol for WebRTC data channels, which is a technology we are probably using right now. And another key feature is the bundling of multiple chunks into a single message. On the bottom right here, we have a typical SCTP protocol. My mouse spinning around. You have a common header, verification tag, checksum, and multiple chunks within a packet. So SCTP loss recovery. The default loss recovery is quite similar to the loss recovery of TCP. It uses two mechanisms. One is a timer-based mechanism, which means, okay, if I don't get any feedback for a particular message within a second, I just start a retransmission, and the specification says 1 second, but modern implementation use 200 milliseconds. And the second algorithm is counting loss indications, which means here's an example. I have a sender and a receiver. I hope you can see my pointer. It's a sender and a receiver. The receiver sends, the sender transmits data number 1, gets an acknowledgement for 1, and sends data number 2. Data number 2 is lost in the network, and the receiver does not receive any message. And then data 3 is sent. The receiver acknowledges data number 3, but reports a gap to the sender. And then the sender discontinues sending chunk number 4, chunk number 5, and each received chunk is acknowledged. And each time the receiver also reports that chunk number 2 is missing. And after 3 gap reports, data number 2 is retransmitted. So, and this is the loss-based recovery. Now, RAG, what's RAG? RAG has originally been developed by Google, and they propose it as a full replacement for the existing error recovery algorithm. So typically in modern transport protocols, you have a bunch of different error recovery algorithms, and Google proposes, okay, we can just use RAG and it replaces all out. Currently, it's an IETF draft in a very late stage. It will soon be published as an RC. It has already been integrated into FreeBSD, Linux, and Windows. And the name RAG comes from recent acknowledgement, which means it's a fast recovery algorithm using time-based inferences. And there's another technique in the RAG algorithm, which is called Taylor's probing. It's not part of the name, but it will, in the future, it will, RAG will be called RAG TLP. And it leverages RAG and sends a probe packet to trigger an ARC feedback. We will have a look at this feature on a later slide. And RAG requires sender-side only modifications. So it only, for TCP, it only requires the default TCP algorithm and the SEC extension, which is default enabled by default for most of the current stacks which are deployed. So how does it work? Whenever you transmit a single packet to the network, you record the precise sending time for every of these packets. So you have a meta information base for every outstanding packet. And whenever a packet has not been acknowledged within a specified time span, for example, 200 milliseconds, and a subsequently sent packet has been acknowledged, the missing packet is retransmitted. So, and another important part is that we have to consider packet reordering. I just said that a packet which has not been acknowledged and a subsequently sent packet has been acknowledged. This doesn't mean that a packet is lost. This does only mean that, yeah, it also can, the reason can also be that we have packet reordering, and RAG considers this packet reordering by reordering window. So this timeout, when RAG sets a packet as overdue, is calculated by using the RAG RTT, which is basically the regular network RTT, and 4 times a so-called reordering window. The reordering window is detected by network metrics. I won't go into detail. And yeah, this is the basic operation, same example as before. We have a sender sending data number 1, gets an acknowledgement for 1, data number 2 is sent, but we don't get an acknowledgement. Data number 3 is now gets now be transmitted to the receiver. The receiver acknowledges packet number 3 and reports packet number 2 as missing. And now the senders transmit 4, but this is not interesting for this case. And now we have the situation that packet number 3, which has been sent subsequently to packet number 2, has been sent and acknowledged. And we have a reordering window timeout. And now packet number 2 is retransmitted. So RAG for SCTP, after we have seen how the RAG algorithm basically works, SCTP supports all required mechanisms out of the box, which are necessary for RAG. This includes SACs. SACs are always enabled in SCTP, and we have another useful feature. Then the receiver always reports duplicates to the sender, and this allows us to get a very precise reordering window calculation. I go back in the slide. When this retransmission would have been too early, because of the reordering window is set too small, the receiver would report packet number 2 as a duplicate, in case it is just reordered and not lost. So I can adjust my reordering window so that in the future I will wait a bit longer to avoid spurious retransmissions. The difference between TCP and SCTP is that in the implementation, we record the transmission times per data chunk. So as I introduced, SCTP bundles multiple data chunks into a single packet. And in the future transmission or in the retransmission, they can be rearranged. So we have to calculate these per chunk and not per packet. And we have a theoretical comparison. We have, considering a sender and receiver scenario, the sender transmits a single packet every send interval milliseconds. So we have a fixed interval between the transmissions, and we have a single event where a packet gets lost. Comparing the regular recovery algorithm and RAG. So as we've seen before, when using the regular algorithm, we have a single RTT, which is required between sending and receiving an acknowledgement. And in between, we have 3 send intervals. When using RAG, we are starting the retransmission after waiting an RTT and the reordering window. And when we compare these two algorithms, we see that if the send interval is below a third of a reordering window, which is by default, the reordering window is a 4th RTT. So we see this equation here. So in the end, in case we are sending at a low interval very quickly data, which is below min RTT divided by 12, the regular recovery algorithm provides a faster loss detection. Otherwise, RAG is better. So we are expecting a better performance for for low sending intervals. We've implemented RAG for SCTP in the OMNET INET simulation environment, and there we have set up a simple testbed consisting of an SCTP sender and UDP sender and router, a common bottleneck, and receiver for SCTP and UDP. The UDP sender and receiver is used to provide some kind of randomness, so we have a small amount of UDP traffic, and to prove or improve our test results. So this is a chart where we compare the good put of a connection in relation to the reordering. So previous evaluation has shown, okay, for regular transmissions at full throttle, both algorithms perform quite well. But in the case of reordering, we see a benefit of RAG. So this is, we send data at wire speed. And when we apply a very small amount of network reordering, the regular dup thresh algorithm goes down, so we get a reduced good put. And in case we're using RAG, we see a quite stable transmission rate, good put rate. So in case we have only network reordering, RAG provides a better performance. As I said in the introduction, RAG has a mechanism called tail-loss probing, which is, in our opinion, one of the most valuable benefits of this algorithm. Tail loss occurs when either the last payload segment or an acknowledgement for the last segment gets lost. And this cannot be detected by dup thresh or RAG. And typically this is recovered by timer-based retransmission, which are extremely slow. And this is a common problem for request response time traffic. For example, take HTTP, and Google has reported that 70% of their losses are recovered by timer-based retransmissions. And how does the tail-loss probing work? After every transmission of a packet, the sender arms a probing timer. And this timeout depends on the smooth RTT and the number of packets in flight. We will see this later, the amount of packets in flight. And when this timer runs out, I will retransmit a single packet just to probe if the peer is still alive or to get some feedback. And our evaluations have shown that this mechanism works quite well, but it tends to mark a large range of packets as lost. I will show a slide, and we will need a burst mitigation. This is an example why we need a burst mitigation. On the left-hand side, we have the transmission sequence numbers. These are the packet numbers for SCTP, and this is the time. And here on the red, the black scale, it's the TSNs which have been sent. We have a sender.
Just a quick reminder: 5 minutes left, including Q&A. Okay.
And the gray line are the packets which are lost. So the black ones are sent and received by the receiver. And here on the red line, these are the acknowledgements. So 100 packets get lost. The receiver does not get any feedback anymore for the packets in flight and sends a TLP, which is a Taylor's probe. And here the receiver gets an acknowledgement, a selective acknowledgement for the TLP. So all these packets which have been sent between are considered as lost, and the sender bursts all these packets into the network. The burst leads to subsequent packet loss and so on, and it takes a lot of time to recover this. The RAG algorithm already suggests proportional rate reduction, and since SCTP already has a built-in burst mitigation, we have used the SCTP burst mitigation, and we have evaluated it and modified the algorithm. And the SCTP burst mitigation is quite as good as the proportional rate reduction, but we had to develop a dynamic burst mitigation algorithm. So if we have a burst caused by a TLP, we limit the number of packets per send call to 4. So whenever I get a suck, I can send 4 new packets, and for subsequent suck 4 new packets. And this is too high if I have shallow bottleneck queues. On the right-hand side, here's the chart. And whenever I see subsequent packet loss, I reduce the packets per send event. So if I send 4 packets and I see subsequent packet loss, I reduce it to 3.75 and so on. And yeah, we'll speed up a bit. The last modification I will introduce in this presentation is using the SCTP IBIT. I've said that TLP timer depends on the number of packets in flight. In case I have only a single packet in flight, I have to consider delayed arcs. Delayed arc is a mechanism that the receiver uses to reduce the amount of selective acknowledgements which are sent to the sender. If I only acknowledge every other packet. So if the sender transmits a single packet and the receiver only receives a single packet, the receiver waits 200 milliseconds or for an additional packet to transmit selective acknowledgement. So before I send a TLP, I have to wait 200 milliseconds. And here is the sender can use extension of SCTP, which is called IBIT. If I set the IBIT to a packet, I request the receiver to immediately acknowledge this packet. So if I use the IBIT, I can drastically reduce the amount of time I have to wait before sending a TLP. And we have compared this. This is a situation where we have only sent a single packet and the single packet is missing. In case we're using the dup thresh algorithm, the receiver, the sender has to wait a second because it only has a chance to recover this loss by using timer-based speed transmissions.
So your time is running out. Can you wrap up quickly? Yeah.
Yep. And if we use REC, we can it would take 200 milliseconds. If we use REC with the IBIT, we will only have to wait RTT, which is in this case 10 milliseconds. So quickly. Thank you.
Any questions? We can have one questions. Seems people are not familiar with this platform or something. Okay, so I got one question that SCTP has numerous extensions or different investigations. Whether your new advanced, let's say, RAC, will provide certain, let's say, fairness against the other SCTP variants or the standard SCTP.
Sorry, can you?
Whether this, you are mainly improve the reliability, right?
Yeah.
You're trying to improve the reliability. Yeah. So in which scenario your work will be comparable than the normal SCTP, and in which particular case you will be much better?
In cases of tail loss and when we have signaling connections. For example, I said we are using SCTP for WebRTC data channels, and these WebRTC data channels are often used for example, steering commands or other signals between two browsers. And in those situations, we only send, for example, every 200 milliseconds or every 500 milliseconds in some cases. And then we are much faster.
Okay, good. Thank you very much for the talk. And let's conclude this. Thank you. Because of the time, we should move on. So the next speaker is, let's see, Miguel, right? Miguel, are you there? Okay, good. Miguel is a PhD student at UPC, so we can see the Zoom not working, or you share the wrong screen, probably. Miguel? So, and his talk title is Preventing Root Leaks Using a Decentralized Approach, an Experimental Evaluation. Okay.
Okay, can you see the slide now?
Yeah.
Okay, thank you. Okay, so good afternoon. Thank you for coming. My name is Miguel Ferriol, and today I will be presenting our work named Preventing Route Leaks Using a Decentralized Approach, an Experimental Evaluation. So first of all, let's start with a little bit of context. So we can define the Border Gateway Protocol, BGP, as the interdomain routing protocol that glues the internet. BGP provides reachability and path selection. However, as the internet evolved and business-oriented autonomous systems started to provide connectivity, there was a need to convey more complex, more rich, and more fine-grained policies. So let's see an example of how these policies are used. In this case, consider two autonomous systems that have a peering relationship. In such relationships, the cost of the connection is shared among the autonomous systems, since the goal is to exchange traffic originated in the peering autonomous systems. for each customer. In this example, when the autonomous system 2 receives a BGP update from each customer, the AS2 propagates it to the AS1. However, when AS2 receives the message from AS3, it must not propagate the route since it comes from a peering connection. If this occurs, the peering autonomous system is now providing transit. So knowing this, one could conclude that BGP is mostly based on trust. This makes it vulnerable to a different number of security threats. And an important BGP security threat are route leaks. So what exactly are route leaks? Route leaks occur when one autonomous system violates the routing policies agreed with another autonomous systems. These policies are based according to the business relationship between them, and as a result of the violation of these policies, traffic can be redirected through the unintended path, traffic can be lost due to suboptimal routing, a prefix can be black holed, or the traffic can be hijacked. BGP route leaks cause important service disruption on the internet. As a recent example, on June 2019, several websites started to have performance issues, including Discord, Amazon Web Services, and privacy management services such as OneTrust. On that day, the AS33154 sent to his customer AS396531 routes for several popular internet destinations, such as Amazon, Facebook, and Cloudflare. Due to misconfiguration, the AS396531 leaked such routes to AS701, another AS396531 transit provider. In a normal scenario, customer should never send such routes. As a result, the AS709 accepted these routes and advertised them, leaking them on a global scale. In turn, some autonomous systems use this new route to reach the popular services, but the AS701 was not suitably equipped to deal with this drastic increase in traffic, resulting in packet loss. As a consequence, there was a major outage of such popular customer-facing services that lasted for roughly 2 hours. So route leaks are a quite simple problem, but really hard to fix. BGP is fundamentally based in trust among the different participant autonomous services. It lacks of cryptographic-based security mechanism, and it also lacks a standard mechanism to communicate these routing policies. So the most, let's say, standard mechanism that BGP provides to communicate routing policies are BGP communities. This is a transitive attribute attached to BGP messages that allow for tagging routes and for modifying BGP routing decision on upstream and downstream. BGP communities can be added, removed, or modified as the message travels from autonomous system to autonomous system. This means that communities can be spoofed, forged, modified, or removed while in transit. As a result, it is well documented that BGP communities represent an important attack vector and can be manipulated to influence routing in an unintended and disruptive way. So what is our proposed solution? So in this work, we take advantage of BGP communities to address the challenges of route leaks. Specifically, we propose an architecture that provides a formal definition of routing policies and the secure mechanism to communicate it to the different participating autonomous systems. We will refer to this as a distributed ledger. So the proposed language used to define the policies contains 5 parameters: the autonomous system number, the community number, the rule that defines the policy to be applied. Most common ones are local preference, prepend, no announce, no export, etc. The value that is only applied to some type of rules, and usually it is an integer and defines the quantity of a given effect. And the to, which tells us what the rule refers to. In example, all autonomous systems of a certain geographical location. Please note that to make sure that the language is expressive enough to cover any BGP policy related to routeleads, we analyzed a wide variety of real-world routing policy datasets. We will talk more about this in further slides. So BGP, I said before, is strongly related to business and trust relationship. As a result, the distributed ledger has a set of requirements to support such a scenario. The different participant autonomous systems on the network must be able to authenticate. The distributed ledger needs to be permissioned. In a BGP scenario, the participant autonomous systems have certain business relationships. This means that the distributed ledger can be governed based on this existing trust. And privacy and confidentiality of transactions and data about different business transactions. The data must be kept private and should only be accessible to intended autonomous systems. So the process used to load a new policy to the ledger is as follows. Execute the transaction and verify its correctness, order transaction via consensus protocol, and validate the transaction against a specific endorsement policy before committing them to the ledger. This endorsement policy specifies which nodes, in this case autonomous systems, or how many of them need to vouch for the correct execution of a given transaction. So this image shows a step-by-step example of our architecture. First, we define an expressive and formal language used to describe routing policy. The language is used by network operators to define their routing policy. This prevents misconfigurations due to the ambiguity of the ill-defined nature of BGP communities. Once the policy has been defined by the network administrator, it is uploaded to the distributed ledger. The distributed ledger is shared among the participant autonomous systems, as it is used to securely communicate the routing policy. We expect that participants are autonomous systems that have already an existing business relationship and thus have an incentive to participate and a certain amount of trust. The distributed ledger makes the routing policy from the source autonomous system available to the participant, to the different participant autonomous systems in a secure way, providing privacy when it's needed and authentication. With this, the destination autonomous system can download the policy and configure it in their existing BGP routers. Specifically, we provide the compiler that translate this formal language used to define the policies to standard BGP route filters. And finally, these BGP route filters are enforcing the policy and preventing those route leaks. So we experimentally analyzed the performance of the proposed architecture. The main goal was to understand how the architecture scales with respect to relevant network parameters. For this, we built a prototype using Hyperledger and Quagga and deployed it in a local testbed for its analysis. So first, we measured the time to compile a community. This is the time it takes to read the policy from the distributed ledger and to transform it onto BGP routing filters. Second, we analyzed the write latency as a function of the number of participant autonomous systems. The write latency includes the time it takes to write a new policy using the formal language into the distributed ledger. And third, we analyzed the chain size with respect to the number of communities stored in the chain. As the table shows, the prototype showed linear scalability with respect to these different three metrics, demonstrated somehow its feasibility. So to validate the proposed approach, we evaluated the prototype in a realistic topology of autonomous system with real-world data. The objective of the experiment was to verify if the system can detect or not and to stop a BGP update that could cause a route leak. So we obtained the BGP routing policy dataset from one step. This is a consulting firm that published a dataset of BGP communities from 27 different autonomous systems. We transform the natural language written dataset onto the our formal defined language. And this figure shows the number of communities defined per autonomous system. It also shows the different types communities found in the dataset. So the topology we use includes 10 autonomous systems, where each autonomous system is configured with a random set of communities from the aforementioned real-world dataset. With this, we emulated a real-world scenario. In this case, we decide for using an endorsement policy that requires at least one signature from each of the 10 participant autonomous system. In addition to this, we artificially introduced a route leak. Besides the policy obtained from the real-world dataset, AS1 also loads a community identified as 333, indicating that a BGP update tagged with this community must not leak. This is stored again in the distributed ledger and automatically configured as BGP route filters in the other autonomous system. Then AS1 sends a BGP update tagged with this community, and the expected behavior is that the configured BGP route filters of the other autonomous system plot the BGP message. To validate this behavior, we manually inspected the propagation of the BGP update message that will result in a leak, and we confirmed that the message is blocked by the installed BGP route filters. In addition to this, we also measured the end-to-end latency, specifically the time elapsed since the routing policy is written until it is compiled and installed as BGP route filters. This process involves the writing, propagation, validation, and the storage of the policy in the distributed ledger. We measure this for each autonomous system in the system, and this figure shows the total end-to-end latency we plot. Where we plot the total time as well as its decomposition of the different states of the prototype: endorsing time, contract execution time, and block time. As the figure shows, the end-to-end latency is in the order of 1 second, and as expected, it is dominated by the endorsing time. So conclusions. In this work, we have presented an open source prototype of a blockchain-based solution to prevent route leaks. Our experimental evaluation shows that the prototype scales linearly with respect to relevant metrics, and that introduces negligible delay when you discount the communication one. Also, we show the prototype in a real-world scenario by preventing a route leak in 10 autonomous system topology. And that's all. If you have any question, please do not hesitate to ask.
Thank you very much, Miguel. Any questions? I don't see a question also in Wura. Maybe I'm the only person that asking questions today for this session. Yeah, do you consider this would be also used for IGP, or not for the, let's say, IBGP, yeah.
Yeah, well, we haven't considered this in IBGP because it's the internal BGP protocol, so this would only be applied in the
heterogeneous ASs.
Yes, correct, with communication between different autonomous systems and not in the same autonomous system. It could be compatible too, but there is no need in this case.
Okay. Okay, thank you very much, everybody. We have about 10 minutes delay of the whole session, but it looks like okay that we catch up for the next session, which starts in 20 minutes. So for the next speakers in the session, please talk with the session chair in the next session, who is Yan Shen. Yeah. Question? Hi, cannot hear you. Okay, then we have a break. Thank you very much, everybody, for the attention for this session. Thank you.